The universe is filled with objects that should not exist, at least not according to the rules we first learned. Stars collapse, matter breaks, gravity wins. And yet, somehow, in the quiet aftermath of that collapse, something impossibly dense and impossibly small survives: a neutron star. A remnant so compact that a teaspoon of its material outweighs mountains, so intense that time and space bend around it, and yet so stable it can spin for millions of years with clockwork precision. Tonight, we drift into the strange truth of these stars that shouldn't exist, and yet somehow do. Their physics, their contradictions, and the quiet mysteries that keep scientists awake long after the telescopes power down. Before we begin, if you're kind enough, a gentle like or a quiet tap on subscribe would mean more than you know. It's a small gesture, but I hold it with deep gratitude, because every quiet sign of support keeps this peaceful corner of the universe glowing for curious minds like yours. Now we drift into the first part of our journey. Part 1. Why the universe allows something as extreme as a neutron star. A neutron star begins with a collapse, the quiet end of a massive sun that once burned millions of times brighter than ours. And yet, instead of disappearing entirely into a black hole, the collapsing core sometimes stops just short of oblivion. It freezes at a density where atoms no longer survive, where electrons and protons fuse and only neutrons remain. To ask why such an object can exist is to ask how matter itself resists the final pull of gravity. When a star reaches the end of its life, its final moments are shaped by a delicate balance that is held for millions of years. Inside its core, fusion once pushed outward with enough force to counteract gravity's endless inward pull. But as the star ages, fuel runs low. Hydrogen becomes helium, helium becomes carbon, and the chain continues until the star can no longer sustain the reactions that kept it inflated. The outward pressure fades, gravity does not. And so, in a silence deeper than anything we've ever known, the star begins to fall in on itself. As the collapse accelerates, the star loses layers of identity. First, its outer shells ignite in brief violent flashes, casting off matter that will one day form planets, moons, or drifting clouds of starlight. But at the center, something stranger unfolds. The core becomes so incredibly dense that atomic structures fail. Electrons are driven into protons, producing neutrons and a flood of neutrinos that escape almost instantly into the darkness. At this moment, the star becomes something fundamentally new, a remnant held together not by heat, but by the most basic quantum forces in the universe. To understand why the collapse stops where it does, you must imagine the quantum world, a place where the rules of everyday life dissolve. At atomic scales, particles are not allowed to sit on top of one another. They resist compression, not through any physical rigidity, but because the laws of quantum mechanics forbid identical particles from occupying the same state. In white dwarfs, this resistance comes from electrons. In neutron stars, it comes from neutrons themselves. Scientists call this neutron degeneracy pressure, a quiet but unyielding barrier that pushes back when gravity tries to compress matter into nothingness. Even as you picture this, imagine the scale of the forces involved. The entire mass of a star heavier than our sun is being squeezed into a sphere only about 20 kilometers wide. A city-sized object with more mass than 500,000 Earths. Gravity at its surface is so strong that if you stood upon it, something no material body could survive, you would weigh billions of times more than you do here. Even light must struggle to escape. And yet, inside that pressure, the neutrons hold. They form a cosmic lattice, a super-dense ocean of nuclear matter that somehow balances the inward crush of an entire star. Neutron degeneracy alone is not the only force at play. The strong nuclear force, the same force that binds the nuclei of atoms, begins to dominate at these densities. In ordinary matter, this force acts over a minuscule range, binding protons and neutrons together inside atoms. But inside a neutron star, its influence spreads across an entire star-sized nucleus, providing an additional layer of resistance against collapse. In this sense, a neutron star becomes something like one giant atomic core, held together not by the structures we know, but by the fundamental forces of nature in their most extreme form. As you breathe in this moment of quiet exploration, consider the strangeness of such an object. Nothing about it aligns with our intuition. Its matter cannot be touched. Its structure cannot be tested directly. Light that leaves its surface carries with it the signature of gravity so strong that time itself slows. In a neutron star's vicinity, clocks run a little differently. Space bends a little more sharply. And yet, despite all this extremity, the star remains stable, sometimes for billions of years. It becomes a cosmic monument to balance, poised between collapse and persistence. The universe allows neutron stars to exist because nature is governed not just by gravity, but by a tapestry of competing forces. Gravity tries to compress, quantum mechanics refuses to yield. The strong force holds neutrons in place. Together, these ingredients create a structure so exotic that it challenges everything we know about matter. And at the same time, it becomes one of the most predictable, precise objects in the cosmos. Some neutron stars spin with extraordinary regularity, turning hundreds of times per second without losing sync for years on end. They become cosmic clocks, more stable than the finest atomic instruments humans have ever built. Yet beneath this stability lies an edge. If the star had been only slightly more massive, neutron, degeneracy and the strong force would not have been enough. Gravity would have crushed everything inward, past the threshold of resistance, forming a black hole. This razor-thin window, the mass range between collapse into a neutron star and collapse into darkness, is one of the universe's most delicate balancing points. Neutron stars exist because their mass is just enough to compress matter into its densest form, but not enough to overwhelm it entirely. And this balance is not permanent. Over long timescales, neutron stars may accrete matter from companions or collide with other stars, pushing their mass beyond the threshold. When that happens, the neutron star's delicate equilibrium fails. In a final, silent instant, the remnant collapses again, crossing the boundary from extreme matter into the full gravitational abyss of a black hole. The neutron star that once resisted the universe's deepest forces disappears behind an event horizon, leaving behind only gravitational whispers. But while they exist, neutron stars hold a kind of quiet authority. They reveal that nature's laws, even under pressure so great that atoms shatter, still find ways to create structure. They show that collapse doesn't always end in darkness. Sometimes it ends in a new form of matter, one that could not exist anywhere else. A star remnant that balances itself on the edge of physical possibility. As we drift deeper into this journey, one question remains. If a neutron star is made almost entirely of neutrons, what strange physics governs the matter inside it? Part 2. The moment a star breaks and why it doesn't break all the way. If we could slow time enough to watch a star collapse, we would see the instant when its atoms fail, when electrons are crushed into protons, forming neutrons in a flash of cosmic violence. But instead of continuing indefinitely outward, gravity meets something unexpected: neutron degeneracy pressure, a silent quantum force strong enough to hold up a star made of pure nuclear matter. To understand this moment, imagine a massive star at the end of its life, its core exhausted after millions of years of fusion. For most of its existence, the star kept itself alive through balance. Every second, nuclear reactions in its core pushed outward with enough force to counter gravity's endless pull. This equilibrium is delicate, quiet, and temporary. But eventually, the star runs out of fuel, the outward pressure weakens, the balance fractures, and the core begins to fall inward. From that point forward, everything happens with unimaginable speed. If you could hover at a safe distance, you'd see the star's outer layers drift for a moment, as if confused by the sudden absence of support. Then, in a wave that moves faster than sound, the entire interior buckles. Matter rushes toward the collapsing core, accelerating under a gravitational pull that grows stronger with each passing millisecond. The atoms inside that core, once stable, once familiar, begin to fail. Their electrons, so light, so fleet, are forced into the protons they orbit. This process, called electron capture, transforms the heart of the star into an immense nuclear crucible. In that transformation, neutrinos burst outward in a flood. These ghost-like particles stream through the collapsing star with almost no interaction, carrying away energy in a silent eruption that surpasses the luminosity of entire galaxies. Yet, despite their intensity, they pass through matter as if through empty air. Nearly all escape into the surrounding darkness within seconds, leaving behind a core that has become something entirely different. The collapse continues. But then, just as it seems gravity will compress the core into a single point, something halts the fall. The neutrons produced during electron capture, each one a tiny quantum object bound by the same rules that shape the behavior of particles within atomic nuclei, begin to resist. Here, quantum mechanics steps forward. According to the Pauli exclusion principle, no two identical fermions, in this case neutrons, can occupy the same quantum state. This rule, invisible in daily life, becomes a wall stronger than steel when matter is squeezed to nuclear densities. This is neutron degeneracy pressure. It is not a force in the traditional sense, not like gravity, not like magnetism. Rather, it is a limit, a refusal of particles to be compressed beyond a certain point. And in the collapsing star, this quantum resistance grows rapidly. Every neutron crowded into the shrinking core pushes back with a kind of pressure that does not rely on heat or motion. It arises purely from the structure of matter at its most fundamental level. The collapse reaches a threshold. The speed of the infalling material slows. Neutron degeneracy and the strong nuclear force begin to dominate. Gravity demands the star continue inward, but the quantum world does not allow it. And so, the infalling matter strikes this newly formed neutron core with titanic force. This moment, this violent collision of outer layers against a suddenly rigid interior, produces the shockwave that powers a supernova. What began as a collapse becomes an explosion. The outer shells of the star rebound, igniting in a catastrophic blaze that sends elements racing into the cosmos. It is in this explosion that the universe gains its heaviest metals: gold, silver, iodine, uranium, each one forged in the heat and pressure of a dying sun. But while the outer layers are cast into space, shaping future worlds, the core remains behind, transformed into a neutron star. The miracle of this object's existence lies in how close it came to becoming a black hole. Just a little more mass, just a slightly heavier progenitor star, and neutron degeneracy would not have been strong enough. The collapse would have continued, past neutrons, past all known forms of matter, into the singularity of a black hole. But with the right mass range, between roughly 8 and 25 times the mass of the Sun, a star can die in such a way that its core stabilizes before crossing that threshold. This boundary between neutron star and black hole is razor-thin on cosmic scales. It depends on the Tolman-Oppenheimer-Volkoff limit, the theoretical maximum mass a neutron star can have before its own gravity becomes overwhelming. That limit is around 2 to 3 solar masses. Any more, and even the combined forces of quantum mechanics and nuclear physics cannot hold gravity at bay. Any less in the neutron star can persist, stable, dense, and impossibly extreme. Inside such a star, matter behaves in ways that challenge our intuition. The crust is solid, crystalline, and incredibly strong, but beneath it exists a fluid of neutrons that moves without friction. Deeper still, the density increases until neutrons begin to overlap, forming exotic states of matter that may include strange quarks or hyperons. These states are theoretical but increasingly supported by observations of neutron star collisions and the gravitational waves they produce. The interior of a neutron star is therefore not simply dense. It is a laboratory for physics that cannot be recreated anywhere on Earth. And yet, for all their complexity, neutron stars remain stable. Their gravity is immense, but so is their internal pressure. Their rotation can be rapid, but not enough to tear them apart. Their magnetic fields can be billions of times stronger than Earth's, but not enough to disrupt the balance within their cores. It is as if the universe has found a point of equilibrium so precise, so unforgiving, that any deviation would erase the object entirely. This narrow balance is what prevents the star from breaking all the way. The collapse is halted not by strength in the classical sense, but by the refusal of particles to violate quantum rules. In this way, neutron stars demonstrate something profound, that the universe's most extreme events are governed not by brute force, but by subtle, invisible principles. Quantum mechanics, a theory designed to explain the smallest particles, becomes the shield that prevents a massive star from collapsing into a singularity. As you reflect on this, consider the silence of that moment. To the star, collapse is not a roar. It is a falling inward, a surrender to gravity interrupted only by quantum limits. If we could stand beside it, again something no body could survive, we would not hear the crumbling of atoms or the merging of particles. We would see only the aftermath, a world made of neutrons, spinning, glowing faintly with the leftover heat of its birth. And so, the star breaks, but not completely. It stops just short of the edge, held aloft by forces that work at the smallest scales, yet shape the fates of suns. In the next chapter, we explore what matter becomes when even atomic structure dissolves, when the familiar world of electrons and orbitals gives way to something stranger, denser, and more mysterious than anything we see in the everyday universe. Part 3. What does matter become at densities beyond imagination? Inside a neutron star, all the ordinary structures we know, atoms, electron shells, chemical bonds, disappear. Matter becomes a single vast lattice of neutrons, packed tighter than the cores of atoms. If you could somehow hold a handful of this material, it would weigh billions of tons. But the deeper question is, how does matter behave when its very identity dissolves? To explore that question, imagine drifting through the star's outer layers, where the transformation from ordinary matter into something unfamiliar begins gradually, almost gently. The crust of a neutron star might only be a kilometer thick, but within it are pressures and densities beyond anything the Earth has ever known. At the surface, nuclei still exist, though crushed and stripped of their electron clouds. The atoms are ionized into bare nuclei arranged in a crystalline pattern, floating in a sea of degenerate electrons. Even here, at the star's softest threshold, matter already behaves like a metal forged from the remnants of an exploded sun. As we descend deeper, the pressure increases until electrons are forced into the nuclei themselves. The boundary between particle types begins to blur. Protons absorb the electrons, becoming neutrons, and atoms lose the last trace of the structures that once defined them. What was once a lattice of nuclei becomes a denser, more homogeneous sea of neutrons. Each step downward peels away another layer of identity. Chemical bonds vanish first, then atomic shells, then even nuclear boundaries begin to stretch, becoming so densely packed that they exert collective behavior rather than acting as individual particles. Here, matter behaves almost like a single entity, a quantum mechanical fluid that ignores the familiar rules of everyday physics. Neutrons, unable to be compressed beyond a certain point, form a rigid but deeply alien lattice. They are held not by electrical attraction or thermal motion, but by the pressure that arises from quantum mechanical exclusion. This neutron lattice may be the closest the universe comes to a perfect quantum crystal, a structure shaped not by energy but by constraint. But this is only the beginning. Continue deeper and the density increases further, reaching levels where neutrons themselves begin to feel the strain. These particles, which are stable inside a nucleus and in the densities of a neutron star's crust, may start to overlap. Their wave functions stretch into one another, blurring any clean separation between them. Matter begins to lose even the distinction between individual neutrons, merging into a superfluid, a frictionless quantum ocean. Superfluidity is one of the strangest states in nature. It means a substance can flow without resistance, without generating heat, without slowing. In laboratories on Earth, superfluids occur only at temperatures near absolute zero and only in delicate small systems like liquid helium. But inside a neutron star, superfluidity becomes the dominant behavior, spreading across volumes larger than cities. the entire interior acts as a fluid with zero viscosity. The star's rotation is not shared smoothly throughout, but distributed through quantized vortices, tiny tornadoes of superfluid neutron matter that arrange themselves in perfectly regular arrays. This quantum structure is not hypothetical. Astronomers have observed glitches in neutron star rotation, sudden jumps in their spin rates, that are best explained by the movement of this superfluid interior. The crust slows due to electromagnetic drag, but the superfluid beneath it continues rotating at a nearly constant pace. Every so often, the superfluid transfers angular momentum abruptly to the crust, causing the star to spin up by a tiny but measurable amount. This is the only direct evidence we have of a superfluid behavior occurring on astronomical scales, and it reveals that inside a neutron star, matter acts more like a single coherent wave than a collection of particles. But even deeper lies an even more mysterious region, one we cannot observe directly, one that no experiment on Earth can fully replicate. This is the inner core, a region so dense that even neutrons, the particles that give neutron stars their name, may not survive in their familiar form. The pressures here exceed anything possible in atomic nuclei, crushing matter to densities perhaps 10 times that of an ordinary nucleus. In this region, neutrons may dissolve into their constituent quarks. Instead of clusters of up and down quarks bound tightly into neutrons and protons, quarks could begin to roam freely, forming a kind of quark-gluon plasma. Some theories propose even stranger states, hyperon matter containing particles with strange quarks, pion or kaon condensates, or super-dense phases where quarks pair up into new collective states of matter not yet observed anywhere else. If this transformation occurs, the core becomes a world without classical boundaries. A single immense droplet of quark matter may fill the star's center, stabilized only by the gravitational crush and quantum rules that hold it in place. Scientists call this possibility a quark core, and though it remains theoretical, subtle clues suggest it may be real. Observations of neutron star masses and radii hint that some stars are too compact to be explained by neutron matter alone. The detection of gravitational waves from merging neutron stars has added more evidence, suggesting that the inner cores may compress and rebound in ways that simple neutron-only models cannot explain. Still, the truth remains hidden. Neutron stars are too far, too small, and too extreme for direct measurement. They keep their secrets behind a wall of gravity and density that no telescope can pierce. The best tools we have are the subtle vibrations, in space-time produced when these stars collide, ripples that reveal a whisper of their interior structure. Even then, the picture remains incomplete. And this uncertainty, this boundary between known physics and the frontier of possibility, is part of what makes neutron stars so compelling. They are natural laboratories for conditions we cannot reproduce. They push nuclear physics, quantum mechanics, and general relativity into the same space, something no earthly experiment can achieve. Inside them, matter may exist in its purest, most fundamental state, shaped by forces that dominate only when the universe compresses itself to its limits. Yet, despite all this strangeness, neutron stars remain stable. They do not dissolve. They do not collapse unpredictably. They persist for millions, even billions of years, rotating, cooling, quietly radiating away the heat of their creation. They show that even at the point where matter's identity dissolves, nature finds a new order, a new kind of structure born from constraints, quantum rules, and the undeniable presence of gravity. As we drift deeper into understanding these objects, one question lingers softly. If matter transforms so completely under pressure, what does that transformation reveal about the universe's smallest building blocks? And more quietly still, what happens if the pressure increases even further, past the limits of neutron matter, into the domain where collapse resumes? Those questions guide us toward the next chapter in our journey. Part 4. Why neutron stars stay round even when spinning, hundreds of times per second. Even as you sit in stillness, neutron stars elsewhere in the galaxy are spinning faster than blender blades, faster than the gears of any clock we can build. yet their surfaces remain nearly perfect spheres. It's because gravity at their crust is so strong that not even rotation, no matter how violent, can distort them by more than a few millimeters. If you could watch a neutron star from a safe distance, an impossible vantage point, yet a useful one, you would see a world in motion. Some rotate once every few seconds, others complete hundreds of rotations in that same time. These are called millisecond pulsars, the most precise rotating objects known. And yet, despite these dizzying speeds, their surfaces do not bulge significantly. Earth, spinning far more slowly, bulges at the equator by more than 20 kilometers. Jupiter bulges by more than 13,000 kilometers. But neutron stars, spinning thousands of times faster than Earth ever could, barely change shape at all. To see why, imagine the balance of forces acting on their surfaces. Every rotating body feels a kind of outward push, centrifugal force, pulling material away from the axis of rotation. It is this force that causes planets to flatten at the poles and widen at the equator. But on a neutron star, that outward push is a whisper compared to the inward pull of gravity. Gravity on a neutron star is so intense that an object falling from just 1 meter above its surface would strike it close to the speed of light. The force binding the star together is overwhelming, far beyond anything rotation can generate. A neutron star's gravity is the result of its compactness. Compress a mass greater than the Sun into a sphere only about 20 kilometers wide, and the result is an inward pull so strong that even light struggles to climb out. The surface gravity is hundreds of billions of times stronger than Earth's. Against this backdrop, centrifugal force, even at 1,000 rotations per second, barely registers as a perturbation. It cannot lift mountains, cannot distort shapes, cannot do more than produce a slight equatorial swelling. In the grand architecture of a neutron star, rotation is merely a breeze brushing against an iron wall. But the star's roundness is not due to gravity alone. Its interior structure also resists deformation. The crust of a neutron star is an exotic material, an ultra-dense lattice of nuclei anchored by neutron-rich matter beneath. It is believed to be the strongest solid in the universe, thousands of trillions of times stronger than steel. Experiments cannot replicate such strength on Earth. It is inferred from theory and from phenomena observed in pulsars such as glitches, tiny jumps in rotation caused by crustal shifts. This crust acts like a shell of nearly unimaginable rigidity. Even if centrifugal forces tried to tear it into an oblate shape, the crust would resist. It would take forces far greater than rotation can provide to crack or deform it significantly. And when it does deform, it cannot stretch upward by more than a few centimeters without shattering, or causing a starquake that would ripple across space in gamma-ray bursts. Even so, neutron stars are not perfectly spherical. Their equatorial radius is slightly larger than their polar radius. But the difference is so small, mere millimeters in many cases, that it is effectively invisible at astronomical distances. In physical terms, it is astonishing. These stars spin so quickly that a point on their equator could be moving at up to 20% of the speed of light, yet their shape responds with a subtlety almost beyond comprehension. To understand just how extreme this stability is, imagine a figure skater spinning. As the skater pulls in their arms, they move faster. This is conservation of angular momentum. A neutron star works the same way. When it first forms from the collapse of a massive star, the shrinking of its core causes the spin rate to skyrocket. Some newborn neutron stars rotate dozens of times per second. Over millions of years, as magnetic braking slows them, they may spin more slowly. But some remain fast enough to outpace any mechanical rotor humans have ever built. If Earth rotated at even a fraction of these speeds, it would tear itself apart. The centrifugal force at the equator would overwhelm gravity, flinging oceans and continents into space. But neutron stars do not share Earth's fragility. Their matter is held together by forces that bind atomic nuclei. Their stability is written in the same physics that prevents neutrons from collapsing into one another, a delicate but incredibly powerful balance between gravity and quantum pressure. Yet there is another piece to this, the role of general relativity. space-time curves dramatically around a neutron star. This curvature changes how rotation is felt, not only by matter on the surface but by the star's overall geometry. In Newtonian physics, rotation and gravity compete directly. But in curved spacetime, rotation is also dragged by the geometry itself. This effect, known as frame dragging, means that space near the star is pulled along with its rotation. The result is that centrifugal effects are partially countered by the gravitational distortion of spacetime. Even the star's extremity becomes moderated by the fabric of the universe itself. As strange as it sounds, the roundness of a neutron star is also a product of its initial formation. When a star collapses into a neutron star, the collapse is almost perfectly symmetric. Gravity acts uniformly, pulling inward from every direction. Unless disrupted by violent instabilities, the star keeps that shape as it cools and settles. Rotation begins afterwards. The star inherits the angular momentum of the collapsing core, but this spin does not reshape it significantly. It simply rotates the sphere that gravity has already carved. Even the fastest spinning neutron stars, those rotating over 700 times per second, remain nearly spherical. Their equatorial bulge may reach a few hundred meters at most, but compared to the star's diameter, it is a tiny deviation. If a neutron star were scaled up to the size of Earth, its surface would be smoother than a polished marble. This near-perfect roundness has real consequences. It allows neutron stars to maintain astonishing rotational stability. A sphere spins without wobble. A distorted object precesses, drifts, and slows. The symmetry of a neutron star's shape is one reason pulsars can rotate for millions of years without significant irregularities. It is why their pulses arrive on Earth like clockwork, predictable down to fractions of milliseconds. And yet, inside this perfect sphere lie profound tensions. Centrifugal forces try to deform the crust, stretching it outward. Magnetic fields twist and bend the interior. Thermonuclear reactions sometimes ripple across the surface. All of these pressures seek to create imperfections, but gravity overrides them all. Even when the crust fractures and quakes, the star as a whole retains its symmetry. What's more, this perfection is temporary. Over time, the star cools, its crust grows thicker, and its rotation slows. The slight equatorial bulge diminishes. The star's shape becomes even more perfect, a sphere refined by time and gravity. And still, the question remains. If rotation cannot significantly distort a neutron star, what happens when forces greater than rotation act upon it? What happens when something external, another star, another neutron star, comes close enough to challenge that symmetry? That quiet tension leads us naturally to the next part of our journey. Part 5. The crust that should shatter but somehow doesn't. A neutron star's crust is a paradox. It should break under the strain of unimaginable gravity and rotation, yet it persists in a stable, crystalline form. Scientists believe it may be the strongest material in the universe, a lattice of nuclear matter thousands of trillions of times stronger than steel, capable of holding mountains only centimeters tall. To understand why this crust exists at all, imagine the moment a massive star collapses, leaving behind its dense neutron core. As the core cools, the outermost layers begin to solidify, not into rock, not into metal, but into something far more exotic. This layer, only about a kilometer thick, becomes a rigid shell composed of atomic nuclei, arranged in patterns that no earthly material can equal. Gravity presses these nuclei together so tightly that electrons are squeezed into a degenerate sea. The result is a kind of nuclear crystal, an ultra-dense solid that forms the boundary between the star's superfluid interior and the vacuum of space. Even calling it a crust feels inadequate. It is less like the thin, fragile crust of a planet and more like the outer wall of a fortress built on forces that dominate at nuclear scales. Yet, astonishingly, this crust works. It holds. It endures. The pressures involved are nearly impossible to imagine. At the surface of a neutron star, gravity is so intense that a sugar cube-sized piece of crust would weigh billions of tons. That alone should make the structure brittle. Any slight deformation, any shift in the lattice should trigger catastrophic failure. And yet observations tell a different story. Neutron stars remain intact as they rotate, flare, and occasionally quake. Their surfaces do not crumble. They do not tear themselves apart. The question is, what gives this crust its strength? What holds it together in spite of the universe's most extreme forces? The answer begins with the nature of the nuclei themselves. In ordinary matter, atomic nuclei are separated by relatively large distances compared to their size, surrounded by clouds of electrons. But in neutron star crusts, the nuclei are forced so close together that their electric charges begin to interact in collective ways. Rather than behaving as isolated structures, they form a repeating lattice, one that shares properties with metals but operates at densities trillions of times higher. These nuclei are incredibly neutron-rich, stabilized by the immense pressure around them. Some models describe them as nuclear pasta, a term that might seem whimsical at first glance, but reflects real theoretical predictions. Sheets of nuclear material, lasagna, tubes, spaghetti, and even more complex topologies. These shapes minimize energy under extreme compression, allowing the crust to maintain stability where any familiar substance would collapse. But the real strength of the crust lies deeper in the quantum mechanics that govern it. The neutrons that permeate the outer layers become partially free, forming a superfluid component beneath the rigid lattice. This superfluid helps distribute stresses more uniformly, acting as an internal cushion for the solid crust above. As rotations slow, as magnetic forces twist, as internal pressures shift, the superfluid can realign itself in ways that prevent large-scale fractures. This interplay between rigid nuclear lattice and flexible superfluid is one of nature's most elegant balancing acts. It allows the crust to absorb disturbances that would tear other materials apart. And yet, the crust is not unbreakable. It can fracture, and when it does, the effects ripple through the entire star. These fractures are known as starquakes. Just as earthquakes relieve stress in Earth's crust, starquakes relieve stress in the neutron star's shell. But the scale is far beyond anything terrestrial. A single starquake can release more energy than the sun emits in centuries, sending gamma-ray bursts and radio flares sweeping through space. These quakes reveal that the crust, while extraordinarily strong, is also under immense tension. Rotation gradually slows due to magnetic braking, causing the crust to adjust its shape. Over millennia, the difference between where the crust wants to be and where it actually is builds up. Eventually, the strain becomes too great, and a fracture occurs. The crust shifts, just a few centimeters perhaps, and the star's rotation may jump slightly. This sudden change is known as a pulsar glitch, and it is one of the most direct pieces of evidence we have for the crust's existence. A glitch is subtle from our vantage point. The pulses of a distant neutron star, which usually arrive with exquisite consistency, suddenly speed up. Then, over days or weeks, they relax back to their original rate. This tiny interruption in rhythm is the fingerprint of the crust cracking and the superfluid interior, transferring angular momentum to the outer layers. It is, in a sense, the crust speaking to us across space. But what is perhaps most extraordinary is how little the crust changes during these events. Despite unimaginable stresses, despite entire regions shifting, the overall shape remains almost perfectly spherical. There are no towering mountain ranges, no deep trenches. Mountains on a neutron star rise no higher than a few centimeters before gravity flattens them back down. Even the crust's strongest imperfections are erased by the overwhelming inward pull. This lack of topography is part of the crust's paradox. It is incredibly strong, yet incredibly thin in the cosmic sense. It must withstand centrifugal forces, magnetic fields stronger than 1 trillion Earth magnets, and the continuous tug-of-war between its own rigidity and the fluid interior beneath it. And still, it holds. To appreciate its strength, imagine compressing a mountain until it is as dense as a neutron star's crust. The pressure would be enough to force atoms into one another, to crush the very space inside their nuclei. Yet even under those conditions, the crust does not lose structural coherence. It behaves like a single unified lattice, an object so harmonious that it resists deformation not through brute force, but through quantum mechanical necessity. Even stranger, the crust may affect phenomena far beyond the star itself. Some theories suggest that imperfections in the crust, tiny irregularities or mountains only millimeters high, could produce continuous gravitational waves. These waves, predicted by Einstein's equations, ripple through space-time itself. Detecting them would reveal information about the crust's exact strength, its texture, and its hidden asymmetries. Observatories like LIGO and Virgo continue to search for such signals, waiting for the faint whisper of a neutron star's rotating imperfections. And if these waves are ever detected, they would offer humanity its first direct glimpse into the nature of matter under the greatest pressures the universe allows. The crust would no longer be a theoretical marvel. It would become a measurable structure, its resilience etched into space-time. But until then, we rely on indirect clues: the steadiness of pulsars, the magnitude of starquakes, the limits of deformation, observational constraints on gravitational wave emissions. Each one hints at a crust that is both impossibly strong and impossibly thin, a cosmic paradox sustained by quantum order and gravitational dominance. The crust should shatter under its own strain, but it doesn't. It bends, it holds, it cracks only in controlled ways dictated by the interplay of forces beneath it, and it continues to do so for millions of years. As we move forward, one question naturally follows. If the crust can withstand these stresses, what happens when the mass of the neutron star exceeds what the crust, and even the neutrons beneath, can tolerate? That quiet frontier leads us into the next part of our journey. Part 6. Why neutron stars don't collapse into black holes. Usually, the only thing standing between a neutron star and a black hole is a balance of forces deep within its core. If the star is slightly too massive, gravity wins, and the star vanishes behind an event horizon. But if its mass falls within a narrow window, quantum mechanics pushes back, forming a state of matter so dense it resists further collapse. This delicate threshold gives neutron stars their improbable existence. To understand this fragile balance, imagine gravity as an endlessly patient sculptor. It works silently, with no haste, pressing everything inward. Throughout the life of a star, gravity is always there, pulling, compressing, waiting. What prevents the star from collapsing during its lifespan is the outward pressure generated by nuclear fusion. Each fusion reaction pushes outward, balancing gravity's inward pull. But when fusion stops, when the star exhausts its fuel, gravity is no longer opposed. It tightens its grip, compressing the stellar core until matter reaches densities far beyond anything we know on Earth. For stars below a certain mass, this collapse stops early. Electrons resist further compression, forming white dwarfs supported by electron degeneracy pressure. But for larger stars, even that resistance breaks. The collapse continues. Electrons merge with protons, forming neutrons, and the core becomes a neutron star, supported now by neutron degeneracy pressure and the strong nuclear force. This is where the delicate threshold emerges. For neutron stars, the inward pull of gravity is nearly strong enough to overwhelm even these quantum mechanical forces. The balance can hold, but only just. It is this unity of quantum stability and gravitational dominance that gives neutron stars their razor-thin existence. The relevant limit, the dividing line between neutron stars and black holes, is known as the Tolman-Oppenheimer-Volkoff limit, named after the physicists who first estimated it in the 1930s. It describes the maximum mass a neutron star can have before even neutron degeneracy pressure can no longer fight gravity's compression. Early calculations place this limit at around 2 to 3 times the mass of our Sun. Modern estimates refine this range, but still land in the same narrow band. Slightly below it, neutron stars survive. Slightly above it, they collapse into black holes. What makes this threshold so astonishing is how tight it is. If a neutron star gains even a small amount of extra mass, perhaps stolen from a companion star, it can be pushed past the limit. A star that has persisted for millions of years can collapse in an instant. No warning, no gradual transition. Gravity simply takes over, crushing the star's interior beyond the reach of quantum forces. But when the mass is right, when the star is heavy enough to collapse into neutron matter, yet not heavy enough to reach the black hole threshold, the result is stable. Matter reaches densities at which new forces emerge. The strong nuclear force acts like a counterweight, not through outward pressure, but through the inherent repulsion that arises when neutrons are pushed too close together. At these densities, the equations of state, the mathematical descriptions of how matter behaves under pressure, become dominated by quantum mechanics. This is the heart of the neutron star's improbable existence, a stalemate between gravity and the most basic rules of the microscopic world. Yet even this balance is not simple. As matter becomes denser, new particles may form. Hyperons containing strange quarks may appear in the center of the star. Pion or kaon condensates may arise. In some models, quarks break free from neutrons entirely, forming a new state of matter, quark matter, at the core. These exotic states can either soften or stiffen the star's interior, altering the star's maximum mass and changing the boundary between survivability and collapse. We do not yet know which of these exotic forms exists in nature, but we do know that whatever occupies a neutron star's center must be able to withstand gravity's relentless inward pull. The core becomes a battleground of physical laws, general relativity shaping the space-time around it, quantum mechanics shaping the internal structure of matter, and the strong nuclear force determining how particles interact at nearly unimaginable densities. This interplay is so delicate that even slight changes in temperature, composition, or rotation can alter the star's fate. Rotation, for instance, can provide temporary stability. A rapidly spinning neutron star generates centrifugal forces that slightly reduce the effective gravity. This can allow a star to exceed the TOV limit by a narrow margin, held up in a sense by its own spin. But when the star eventually slows, this extra support disappears. Collapse can ensue. Binary systems offer another glimpse into this precarious balance. Some neutron stars orbit companions, other stars are white dwarfs, and siphon matter from them. This steady accumulation gradually increases the neutron star's mass. If it gains too much, the balance fails and the star collapses. Yet, remarkably, many such stars maintain a stable existence despite constantly accreting new material. They hover near the threshold, sustained by the internal physics that resists collapse. The narrow window of stability is also reflected in neutron star mergers. When two neutron stars spiral together, the combined mass often exceeds the TOV limit. For a brief moment after their collision, milliseconds perhaps, the merged object may form a hypermassive neutron star, stabilized temporarily by extreme rotation and thermal pressure. But as this support fades, collapse becomes inevitable. The remnant disappears, forming a black hole in a sudden silent implosion. These events produce gravitational waves, ripples in spacetime that carry information about the star's internal structure. When detectors like LIGO first captured these waves, they gave us a glimpse of the boundary between neutron stars and black holes. The waves bore the imprint of a star whose very matter was fighting collapse. In the milliseconds before the merger completed, the star's shape and response revealed how close it was to the limit. In this way, neutron star physics becomes not just theory, but something we can measure in the fabric of spacetime itself. Despite their precarious balance, neutron stars remain remarkably stable once formed. Their mass distribution, internal pressures, and equation of state settle into a long-lived equilibrium. They rotate steadily, they cool slowly. They persist for billions of years unless acted upon by outside forces. This persistence is part of their quiet beauty. A neutron star represents the victory of quantum mechanics over gravity, up to a point. It is a testament to nature's ability to find equilibrium even under conditions that should, by all intuition, produce destruction. Yet the boundary remains. Neutron stars live on the edge. They exist only because their mass lies within one of the narrowest windows in astrophysics. A little lighter, and the star would not form a neutron core at all, instead becoming something more ordinary. A little heavier, and nothing could prevent collapse. So why don't neutron stars collapse into black holes? Because their cores, governed by quantum rules and nuclear interactions, push back just enough, only enough, to resist gravity's final embrace. But the question that lingers, softly and persistently, is this. What happens to the star when the forces that sustain it begin to shift, or when the universe asks it to endure more than it can bear? That quiet threshold leads us deeper into the mysteries of mass, pressure, and fate in the next chapter. Part 7. Why neutron stars spin faster. As they age, a dying star slows as its fuel burns, but its remnant, the neutron star, often spins faster over time. This happens because neutron stars behave like cosmic skaters pulling in their arms. As they lose heat and contract, their rotation accelerates. Some whirl hundreds of times per second, their magnetic fields sweeping across space like lighthouse beams. To understand this acceleration, picture the final moments of a massive star before it collapses. For millions of years, the star rotated slowly, its enormous radius spreading its angular momentum across a vast volume. When gravity overwhelms the core and forces it inward, something profound happens. The radius shrinks dramatically, but angular momentum is conserved. It is a fundamental principle of physics, one that governs everything from orbiting planets to spinning dancers. A star that once spanned hundreds of thousands of kilometers collapses into an object only about 20 kilometers across. That shrinkage, by a factor of tens of thousands, means the rotation rate must increase by the same enormous factor. A star that once turned gently may now whirl dozens of times each second. The collapse is the first great acceleration. But what is remarkable is that the neutron star can continue to speed up long after its birth. The key lies in the physics of heat, magnetic fields, and the slow loss of rotational energy over long cosmic timescales. When a neutron star is born, it is scorching hot, its interior still radiating the leftover heat from the supernova explosion. Over time, it cools, and as it cools, the matter inside contracts slightly. Even a contraction of a few centimeters is enough to alter the rotation rate. Like a figure skater drawing in their arms by just a few inches, the neutron star spins a little faster to conserve angular momentum. But this is only part of the story. Neutron stars are not simple solid objects. Their interiors contain superfluid neutrons, quantum matter that behaves in ways no earthly material can replicate. This superfluid stores angular momentum in discrete units called vortices. As the star cools and contracts, these vortices rearrange themselves, shifting and migrating, gradually transferring their stored angular momentum to the crust. The result is a slight but steady increase in the outward rotation we can observe. This interplay between the crust and the superfluid interior also leads to something called glitches, sudden jumps in a neutron star's rotation rate. These glitches represent moments when the superfluid transfers angular momentum abruptly to the rigid crust. In the moments after a glitch, the star spins just a little faster, as if taking a sudden sharp breath. Over days or weeks, it relaxes back to its steady rate. But across millions of years, the net change is an overall acceleration, subtle but measurable. Some neutron stars, however, achieve even greater spin speeds. These are known as millisecond pulsars. They rotate so fast, hundreds to over 1,000 times per second, that their equators move at a significant fraction of the speed of light. Yet, these extreme speeds are not reached simply from contraction. Instead, they involve a quiet, cosmic partnership. Many neutron stars exist in binary systems with ordinary stars or white dwarfs. Over time, material from the companion star can drift toward the neutron star, pulled in by gravity. As this material spirals inward, it forms an accretion disk, heating up and generating powerful radiation. But as the disk tightens, it also transfers angular momentum to the neutron star itself, spinning it faster and faster. It is a process akin to someone running in circles around a merry-go-round, pushing it a little more with each lap. Slowly, continuously, the neutron star's rotation rate increases. In extreme cases, this spin-up can produce a neutron star rotating nearly 1,000 times per second. These are the fastest spinning stable objects in the universe. They owe their speed not only to contraction, but to millions of years of siphoning material and angular momentum from their companions. And yet, for all this acceleration, neutron stars also lose energy. As they rotate, they generate intense magnetic fields, sometimes trillions of times stronger than Earth's. These fields anchor the star's rotation, sweeping through space as the star spins. Charged particles caught in the field radiate energy. Over time, this radiative loss acts like a brake, slowing the rotation. This braking is gentle but constant, causing neutron stars to gradually lose rotational energy. It is the reason why some young pulsars slow down over time, their pulses becoming more spaced out as the star ages. But cooling and contraction often counteract this slowing. The interplay between these opposing forces, magnetic braking slowing the star, contraction speeding it up, determines the exact evolution of a neutron star's spin rate. Millisecond pulsars, despite their incredible speed, are often among the oldest neutron stars. Their rapid rotation is a sign not of youth, but of a long history of accretion and angular momentum exchange. They have been spun up, polished by time and by the gravitational nourishment of their companions. This rotational behavior has profound consequences. The faster the star spins, the more stable it becomes, up to a point. Rapid rotation can provide additional support against gravitational collapse, temporarily raising the maximum mass the neutron star can safely hold. But this support is precarious. As millisecond pulsars age and gradually lose angular momentum through radiation, they may approach a threshold. If their mass is near the limit, even a slight slowdown could remove the rotational support and trigger collapse into a black hole. This possibility, of stars quietly waiting for the moment when rotation no longer staves off collapse, adds a layer of quiet tension to the story of neutron stars. Their spin is not simply a characteristic, it is a stabilizing force, a guardian of their continued existence. And yet, despite these underlying dangers, neutron stars remain remarkably precise. Their rotations, especially those of millisecond pulsars, are so stable that they can be used as cosmic clocks. Astronomers have measured some pulsars that lose only a microsecond of rotational regularity over decades. This stability arises precisely because of their elevated spin. Faster rotation leads to symmetry. Symmetry leads to stability. Even the way they emit radiation reflects their rotation. As their magnetic poles sweep across space, beams of radio waves, X-rays, or gamma rays fan outward. When such a beam crosses Earth, we observe a pulse. The name pulsar derives from this steady ticking, this beating of a cosmic heart, and the speed of that ticking is tied to the star's rotational energy, the same energy that grows stronger as the star ages and contracts. Some neutron stars undergo even more exotic spin-up processes. In rare cases, they may absorb planets or smaller stars, gaining bursts of angular momentum. These events are transient but powerful, adding further layers of complexity to the star's long-term rotational evolution. And yet, through all of this complexity, one quiet truth emerges. Neutron stars are shaped by change. They evolve, they cool, they contract, they interact with their surroundings. Their spin is not fixed. It is a living characteristic, unfolding over millions of years. As they age, they often become faster, not slower, because the universe continually finds ways to tighten their structure, conserve their angular momentum, and give them renewed bursts of rotation. They are cosmic engines, spinning not out of chaos but out of an intricate and persistent balancing of forces. And with that delicate balance comes a deeper question. If neutron stars can spin faster as they age, what shapes the magnetic fields that accompany this rotation? How do those fields evolve, strengthen, and sometimes twist into the violent extremes observed in magnetars? These questions guide us into the next chapter of our quiet journey. Part 8. How a magnetic field becomes a monster. Magnetic fields around neutron stars are billions of times stronger than Earth's. These fields can wrench atoms apart, twist light into strange paths, and hurl particles across space at nearly the speed of light. A neutron star's magnetic heartbeat is one of the most powerful natural forces ever discovered. To understand how such a magnetic monster is born, we begin long before the neutron star itself takes shape, inside a massive star that has lived a full and fiery life. During its lifetime, the star generates magnetic fields through the motions of charged particles within its plasma-filled interior. These fields twist, shift, and intensify as the star ages, influenced by rotation and convection. For most stars, including the Sun, these fields remain strong but manageable. They manifest as sunspots, flares, and occasional bursts of high-energy radiation. But when a massive star dies and its core collapses into a neutron star, something extraordinary happens. The magnetic field does not simply persist, it becomes compressed. Magnetic flux, the total amount of magnetic field passing through a surface, is conserved during the collapse. As the star's radius shrinks by a factor of about 100,000, its magnetic field intensifies accordingly. A field that once reached 1,000,000 Gauss may suddenly surge to 1,000,000,000 Gauss. This alone is enough to tear molecular bonds apart and distort the vacuum around it. Yet, compression is only the beginning. After the collapse, the newborn neutron star begins to rotate, often hundreds of times per second. This rotation, coupled with the star's conductive interior, acts like a dynamo, similar in principle to Earth's magnetic field generator, but vastly more intense. Charged particles in the crust and core move at incredible speeds, amplifying and stabilizing the magnetic field. The star becomes a kind of cosmic generator, with its magnetic field lines anchored deep within the nuclear lattice of the crust. But unlike Earth's gentler field, a neutron star's field is violent, structured, and deeply anchored. The surface is threaded with magnetic lines strong enough to lift and accelerate particles outward along the poles. These particles, electrified and guided by the magnetic field's shape, emit radiation as they spiral outward. This is what gives rise to pulsars, the sweeping beams of electromagnetic energy that we observe as rhythmic pulses from across the galaxy. In this environment, light does not behave normally. A field of 1,000,000,000 Gauss is strong enough to polarize the vacuum itself, forcing photons to travel in certain directions. Even empty space becomes a medium, a quantum fabric that bends under magnetic pressure. This effect, known as vacuum birefringence, has been observed only indirectly, yet it is a clear sign that neutron star magnetism lies at the very edge of what physical laws allow. Still, the most terrifying magnetic fields of all belong to a special class of neutron stars called magnetars. These objects are rare, perhaps only a few dozen exist in the Milky Way, but they redefine what magnetic strength can mean. Magnetars possess fields up to 1,000 times stronger than typical neutron stars. Their fields are so powerful that they can deform the crust, twist it into new shapes, and trigger violent starquakes. These quakes release bursts of gamma rays so bright they can briefly overwhelm detectors across the solar system. Magnetars form when the conditions inside a neutron star align in a certain way: rapid rotation at birth, high internal temperatures, and a specific arrangement of magnetic flux. It is believed that shortly after their formation, vigorous convection in the newborn neutron star creates a stellar dynamo far more powerful than anything in an ordinary pulsar. The result is a magnetic field so immense that it distorts the star's crust, generating continuous strain. This strain builds over years or decades until it becomes too great. The crust snaps. In that instant, twisted magnetic fields realign, and the magnetar unleashes a burst of energy that can outshine entire galaxies for a fraction of a second. These are the most energetic events observed in the universe, aside from supernovae and collisions between neutron stars themselves. The field does not exist only on the surface. Deep inside the star, magnetic lines may thread through the superfluid core, creating a complex web of currents and interactions. As the star rotates, these internal structures can shift, generating localized tensions in the crust. The magnetic field becomes both the star's skeleton and its tormentor, holding it together while also threatening to tear it apart. But why do some neutron stars become magnetars while others remain ordinary pulsars? The answer lies in subtle differences during formation. A neutron star born with extremely rapid rotation may generate a strong enough dynamo to produce magnetar-level fields. If it cools too quickly or fails to rotate fast enough, the dynamo shuts off prematurely, leaving a weaker magnetic field behind. It is a delicate race between heat, rotation, and turbulence, one that decides whether the newborn star becomes a cosmic lighthouse or a cosmic monster. Once generated, however, magnetar fields decay over time. They push against the crust, fracture it, and bleed energy into space. Over thousands of years, the field weakens, leaving behind a quieter neutron star. Even so, the remnants of its former strength can linger. A magnetar, only a few tens of thousands of years old, may still emit bursts of radiation that dwarf anything a typical pulsar could produce. Even ordinary neutron stars, however, wield magnetic fields that shape their environment dramatically. These fields carve out magnetospheres, regions around the star where charged particles are trapped and accelerated. These magnetospheres can extend hundreds of thousands of kilometers into space. Any matter that enters them, gas from a companion star, dust from the interstellar medium, even the remnants of the star's own supernova, becomes electrified, heated, and funneled along the magnetic poles. Along these poles, the star emits beams of radiation. As it rotates, these beams sweep across space. If Earth lies in their path, we see the pulses. If not, the neutron star remains hidden to us, its magnetic heartbeat detectable only through higher energy emissions. But whether we see them or not, these beams sculpt the surrounding space, influencing particles, magnetic fields, and radiation patterns across vast distances. The strength of these magnetic fields is not merely a matter of size or density, it is a fundamental property of neutron star matter. Electrons and protons are locked together in dense nuclear arrangements, and the intense gravity and pressure of the environment align currents in ways impossible anywhere else. It is as though the star itself becomes a single giant conductor, spinning and glowing with magnetic energy. In some cases, magnetic fields may even deform the star's shape slightly. If the field is internally twisted or asymmetric, it can alter the distribution of mass inside the star. This creates a continuous, non-axis symmetric motion that may generate gravitational waves. Such waves are faint but persistent. Detecting them could reveal the internal magnetic structure of neutron stars with unprecedented clarity. Yet despite their monstrous power, magnetic fields decay. A neutron star's magnetic strength diminishes as it ages, dropping from trillions of Gauss to more modest values over millions of years. Some stars become too weak to generate powerful radiation. They turn quiet, fading into the background of the cosmos, their youthful storms replaced by an elderly calm. What remains, even after the magnetic ferocity subsides, is the evidence imprinted on the star's crust, scars of ancient flares, disruptions caused by magnetic twisting, fractures that once shook the star to its core. And so the story of a neutron star's magnetic field is one of birth, growth, power, and eventual decay. It is the story of how extreme environments magnify ordinary physics into something overwhelming. It is the story of how magnetic energy shapes the life cycle of some of the most enigmatic objects in the universe. But as we reach the edge of this magnetic frontier, a new question emerges, soft but persistent. If magnetic fields can grow strong enough to twist space and time, what strange patterns emerge when a neutron star's rotation and magnetic forces align with perfect precision? That quiet mystery guides us to the next chapter of our journey. Part 9. Pulsars. Why some neutron stars become cosmic clocks. When a neutron star's magnetic field aligns just right, beams of radiation sweep across the cosmos. Each rotation sends a pulse of light toward Earth, ticking with the regularity of an atomic clock. These pulsars reveal the star's spin, its age, its interior structure, and sometimes even the presence of hidden planets orbiting their dead suns. To understand why pulsars behave like cosmic clocks, imagine a lighthouse on a dark, quiet shore. The light rotates, sweeping across the ocean in a rhythmic pattern. You do not see the lighthouse itself, only the beam, appearing and disappearing with perfect inevitability. A pulsar works in much the same way. The neutron star itself remains invisible to us, a tiny remnant nearly swallowed by the vastness around it. But its magnetic poles emit beams of radio waves, X-rays, or gamma rays. As the star spins, these beams trace circular paths, and if Earth lies in their sweep, we see them as pulses. This mechanism begins with the neutron star's magnetic field, a field so strong it functions like an immense cosmic engine. The magnetic axis is rarely aligned with the rotation axis. Instead, it tilts, forming a rotating magnetic dipole. Charged particles move along these magnetic field lines, accelerating to near-light speeds. In doing so, they emit radiation outward from the magnetic poles. These poles, moving with the spin, sweep through space like the hands of a cosmic metronome. A typical pulsar rotates dozens of times per second. Some rotate far faster, hundreds of revolutions each second, producing pulses that arrive with such precision that astronomers sometimes use them to calibrate clocks on Earth. The timing stability of these pulses is remarkable. A well-behaved millisecond pulsar may lose or gain less than a millionth of a second over years. Nature has created a mechanism more stable than most human technology, and it does so not through gears or quartz crystals, but through immense gravitational forces and quantum mechanics playing out inside a collapsed star. This precision arises from the incredible rigidity and symmetry of a neutron star. Because the star is nearly spherical, with a mass distribution stabilized by gravity and nuclear forces, it rotates without wobble. Its crust and superfluid interior work together as a single system. Once spinning, its rotation persists with minimal change, slowed only by magnetic braking over long timescales. This stability is the hallmark of a pulsar, a tiny remnant of a supernova whose rotation has become so smooth, so consistent, that it mirrors the ticking of a perfect clock. The pulses we observe reveal not just the spin, but also the internal structure of the star. When a pulsar glitches, a sudden jump in rotation, it reflects a shift in angular momentum from the superfluid interior to the crust. These glitches are windows into the behavior of matter at nuclear densities, hints of how neutrons, vortices, and quantum fluids interact beneath the surface. Each glitch is a seismic event in a world where mountains rise no taller than a sheet of paper. Pulsars also slow down gradually due to the loss of rotational energy. Their magnetic fields act like brakes, emitting radiation that bleeds energy away. This slowdown rate provides clues to the star's magnetic strength and age. Young pulsars rotate quickly and lose energy rapidly. Older ones rotate more slowly, their beams weaker and less erratic. Yet through all this evolution, the pulses remain predictable. Some pulsars emit in multiple wavelengths, their beams carrying different signatures at radio, X-ray, and gamma-ray energies. These multi-wavelength signals help astronomers map the geometry of the magnetic field and the shape of the emission zones. Even the slight curvature of spacetime around the pulsar affects these beams. In extreme cases, light can bend around the star, allowing us to see regions of the surface that would otherwise be hidden. A pulsar, through its predictable flicker, becomes a laboratory for studying both matter and gravity in their most extreme forms. The most extraordinary examples are millisecond pulsars. These neutron stars have been spun up by accreting matter from a companion star. As they absorb material, they also absorb angular momentum. Over millions of years, this process accelerates the neutron star until it spins hundreds of times per second. The magnetic field, stretched and twisted by this rapid rotation, becomes more stable. The beams sweep with unprecedented regularity. Millisecond pulsars are the universe's most reliable clocks, ticking with a consistency rivaling the best instruments humanity can build. It is through pulsars that astronomers discovered some of the first exoplanets. In 1992, researchers observed tiny variations in pulse timing from a pulsar named PSR B+12. These variations were so consistent, so rhythmic, that they could only be explained by orbiting planets tugging on the neutron star. In a cosmic irony, the first confirmed planets beyond our solar system were found not around a living star, but around a dead one. These planets must have formed from the debris of the supernova, quietly orbiting a remnant that blinks like a cosmic beacon. In binary systems, pulsars become even more intriguing. A neutron star paired with another star or another neutron star will introduce gravitational effects that alter pulse timing. These timing variations can reveal the orbit of the companion, the mass of both stars, and even the curvature of spacetime around them. In some rare systems, pulsars allow us to test general relativity with extraordinary precision. The first indirect detection of gravitational waves, long before LIGO, came from measuring the orbital decay of a binary pulsar system, their pulses revealing that the stars were losing energy exactly as predicted by Einstein. Pulsar timing arrays, networks of pulsars observed simultaneously, may one day detect the slow rumble of gravitational waves passing through the galaxy. These waves, produced by supermassive black holes orbiting each other, would stretch and compress spacetime subtly, altering the timing of pulsar signals. If this technique succeeds, pulsars will become not just clocks but detectors, living instruments built by the universe itself. Yet, pulsars are not immortal. As they age and lose energy, their rotation slows, the magnetic field weakens. Eventually, the pulses fade, and the neutron star becomes quiet. It becomes a radio-silent remnant, detectable only through thermal radiation or interactions with nearby matter. But for millions, even billions of years, pulsars endure as lighthouses of the cosmos, steady, unblinking, whispering the rhythm of the stars. Every pulse is a moment of cosmic communication, a signal that has traveled across unimaginable distances to reach us. When we detect them, we are hearing the heartbeat of an object that should not exist, yet does. A remnant of a star that died long before humanity existed. And as we listen to these cosmic clocks, another question rises softly, almost imperceptibly. If pulsars can reveal the timing and structure of a neutron star so precisely, what can their rhythms tell us about the deeper, hidden states of matter within them? In that question lies the path toward our next chapter. Part 10. What lies beneath the crust? The ocean of superfluid neutrons. Beneath the rigid outer shell of a neutron star lies a layer unlike anything on Earth, a superfluid ocean of neutrons. This fluid flows without friction, without heat, without resistance. It can rotate in quantized vortices, forming patterns that obey the strange rules of quantum mechanics on a macroscopic scale. To understand this mysterious layer, imagine descending through the neutron star's crust, a crust already stronger than any material known, already so dense that atomic structures have collapsed. As you pass through the final crystalline layers, there is a moment, subtle and profound, when matter ceases to behave like a solid lattice and begins to act like something far stranger. Neutrons that were previously locked into rigid positions slip free, pooling into a fluid that cannot be compared to water or metal or any terrestrial substance. Instead, it becomes a superfluid, a quantum liquid that behaves as though the usual rules of matter no longer apply. In this superfluid ocean, neutrons move collectively, not individually. Every particle participates in the same quantum state, forming a vast, coherent wave. Friction disappears entirely. No flow of this liquid ever slows down. If it were to swirl around the core, that swirl could persist for millions of years without losing a fraction of its motion. It is motion without loss, perpetual, silent, and perfectly smooth. The superfluid's behavior becomes even more incredible when the neutron star rotates. In ordinary fluids, rotation creates swirling eddies, turbulence, chaotic movement. But a superfluid cannot rotate like that. Quantum mechanics demands order. Instead of rotating as a continuous whirlpool, the superfluid breaks its rotation into discrete units called quantized vortices. These vortices are tiny, thread-like regions where the superfluid's orderly state briefly breaks, allowing rotation to exist within strict quantum rules. Imagine looking down at the neutron star's interior with senses attuned to the quantum world. You would see a forest of these vortices, thousands, millions, perhaps billions of them, arranged in a perfectly regular pattern. They form a lattice of rotational threads, evenly spaced, each carrying a precise fixed fraction of the star's angular momentum. As the star spins, the vortices shift and migrate, sliding like silent gears inside the superfluid ocean. Their arrangement reveals the star's rotation rate with perfect fidelity. These vortices are not just theoretical curiosities. Their movement influences the entire star. They anchor the superfluid to the crust through tiny interactions, allowing the superfluid interior and the solid outer shell to rotate almost, but not completely, together. Over time, as magnetic braking slows the crust, the superfluid beneath it retains its original speed, storing angular momentum like a hidden reservoir. This mismatch builds tension, and eventually, the vortices rearrange themselves in a sudden, synchronized migration. When they do, they push angular momentum into the crust. This event is what produces a glitch, a tiny but abrupt increase in a pulsar's rotation rate. From Earth, these glitches appear as sudden jumps in timing, moments when the pulsar's cosmic heartbeat skips forward. Although the change is minuscule, often a few parts in a million, it is enough to reveal the presence of the superfluid beneath the crust. No classical explanation fits. Only the silent, frictionless movements of the superfluid ocean can account for such behavior. Deeper still, below this ocean of superfluid neutrons, lies an even more exotic region where protons may form their own superconducting fluid. A superconductor is a substance that carries electric current without any resistance, a concept familiar from advanced laboratory experiments on Earth. But inside a neutron star, the superconducting fluid is woven together with the superfluid neutrons, forming a dual quantum state. The motions of one influence the motions of the other. Vortices in the superfluid couple with quantized magnetic flux tubes in the superconducting region. Together, they create a dynamic interior structure that shapes the star's rotation, magnetic field evolution, and long-term cooling. It is here, in the depths of the star, that its long-term behavior is written. The superfluid flows silently, moving heat and energy with perfect efficiency. If a neutron star were made of ordinary matter, hotspots would develop, heat would accumulate, and the star would cool unevenly. But because of the superfluid, heat spreads smoothly throughout the interior, allowing the entire star to cool uniformly. This is why neutron stars can radiate away their leftover heat for millions of years without sudden temperature shifts. The properties of this ocean also shape the magnetic field in subtle ways. As the star cools and its superconducting core evolves, the magnetic flux tubes shift, causing the star's magnetic axis to drift. This drift can slowly alter the pulses we observe from Earth, creating faint changes in timing that tell astronomers the star's magnetic field is alive, restless, evolving. Just as Earth's magnetic field wanders over centuries, a neutron star's magnetic axis shifts over millennia, but with far greater intensity. Even more remarkable is that the superfluid may contain clues about the fundamental forces of nature. The behavior of neutron matter at these densities cannot be replicated in laboratories. Particle accelerators can reach high energies, but not the high pressures or long-term stability required to mimic neutron star interiors. Every observation of a glitch, every measurement of a pulsar's temperature, every gravitational wave from a neutron star collision becomes a data point, a message from matter under the most extreme conditions the universe allows. Though we cannot see this superfluid directly, its effects ripple outward. For example, when two neutron stars spiral toward each other and merge, the behavior of their interiors affects how quickly they lose energy through gravitational waves. These waves carry signatures of the superfluid interior, allowing scientists to infer its stiffness, its compressibility, its ability to sustain tidal forces. As detectors improve, we may one day read these signatures with enough precision to map the behavior of the superfluid layer itself. But perhaps the most haunting aspect of the superfluid ocean is how serene it is. Above it, the crust cracks, quakes, and groans under magnetic strain. Outside it, the magnetosphere bursts with radiation, but below the crust in the hidden depths, the superfluid remains undisturbed. Its flow is eternal. Its motion is smooth. It is the calm heart of a violent object. If we could somehow witness a neutron star from within, feeling nothing, floating in that frictionless medium, we would experience an absolute stillness, unlike anything in the familiar world. No turbulence, no sound, no resistance, just a quiet, perfect fluid that has existed unchanged since the star's birth. And yet this quiet fluid may determine the star's ultimate fate. As the star cools further, as rotation slows, as the magnetic field shifts, the interactions between the crust and the superfluid become more pronounced. If a neutron star gains mass, perhaps from a binary partner, the superfluid may respond in complex ways, redistributing angular momentum or altering the star's structural integrity. These internal dynamics can bring the star closer to or farther from collapse. So even though the superfluid is silent, it is not passive. It is the engine of the star's evolution, the hidden architect of its timing, the regulator of its thermal life, the keeper of its deepest mysteries. And as we drift deeper into this story, one quiet question emerges. If the superfluid beneath the crust can store and release angular momentum, what happens when the star experiences sudden, large-scale shifts, events far more violent than glitches? This leads us to the strange, unpredictable phenomena that neutron stars sometimes display next. Part 11. Why neutron stars suddenly glitch. Every so often, a neutron star stutters. Its rotation rate jumps slightly, then settles back into its normal rhythm. Astronomers call these events glitches, and they reveal something extraordinary. The superfluid interior and the solid crust can momentarily decouple, slipping past one another in a brief, silent quake. To understand this strange behavior, imagine a neutron star as a layered world. On the outside sits the rigid crust, thin by cosmic standards but unimaginably strong, a crystalline shell of nuclear matter. Beneath it lies the superfluid ocean, a frictionless sea of neutrons that rotates with perfect smoothness. These two layers are bound together, but only loosely. They influence one another, but they do not lock into perfect synchrony. The crust can spin slightly slower. The superfluid can spin slightly faster. And between them lies a tension that builds over centuries. As a neutron star emits radiation, radio waves, X-rays, gamma rays, it loses rotational energy. Its magnetic field acts as a brake, gradually slowing the crust. But deep below, the superfluid does not slow easily. It has no internal friction, no viscosity, no mechanism for gradually surrendering its angular momentum. So while the crust decelerates, the superfluid ocean continues rotating at almost its original speed. Over time, the difference between the crust's rotation and the superfluid's rotation becomes enormous on quantum scales. Angular momentum accumulates, stored invisibly in the superfluid's quantized vortices. These vortices, millions of thread-like channels of rotation, anchor themselves to irregularities in the crust. They cling to tiny imperfections locked in place. But as the crust continues to slow, the vortices stretch. The tension becomes immense. Eventually, like overloaded springs, they cannot hold any longer, and in a single instant, no sound, no heat, no warning, they snap free. When the vortices unpin, they rush inward toward the star's axis of rotation. This inward migration transfers angular momentum from the superfluid to the crust. The crust jumps forward in rotational speed, suddenly spinning faster. This is the glitch. From Earth, it appears as a sharp, tiny spike in the pulsar's timing. A single pulse arrives slightly earlier than expected. Then another, and another. Over the next hours, days, or sometimes weeks, The star gradually returns to its previous rhythm as internal forces redistribute themselves. The signature is unmistakable, a sudden jump followed by a long, graceful recovery. Glitches are among the most revealing features of neutron stars because they allow us to glimpse processes otherwise hidden under kilometers of dense matter. They show us that the crust is not perfectly rigid and that the superfluid beneath it behaves as a vast quantum engine, storing and releasing angular momentum on timescales far beyond human experience. But vortices snapping free from the crust are not the only cause of glitches. In some neutron stars, especially the younger and hotter ones, glitches may arise from crustal fractures. Their magnetic fields twist the crust into strained, tortured configurations. As the internal magnetic field reconfigures itself, it can place enormous stress on the crust. When that stress reaches its breaking point, the crust shatters in a sudden starquake. In such an event, the crust's moment of inertia changes abruptly. The star's rotation depends on its moment of inertia. A sudden change causes an equally sudden shift in rotation rate. It is as if the neutron star adjusts its shape, microscopically but violently, and the spin changes instantly in response. This too generates a glitch, though its profile may differ from one triggered by superfluid vortex migration. These two mechanisms, vortex unpinning and crustal fractures, may act together. A starquake could trigger a rearrangement of superfluid vortices, or vortex motion could stress the crust enough to break it. In the delicate interplay of superfluid and solid, one event can cascade into the other. The neutron star becomes a single integrated machine, every part responding to every other part in ways that defy classical intuition. Glitches are often followed by a relaxation phase, where the star's rotation gradually returns to its previous rate. This recovery offers important clues. A fast recovery suggests tight coupling between the crust and one region of the superfluid. A slow recovery reveals deeper, more sluggish layers. Different pulsars show different combinations, meaning no two neutron star interiors are exactly alike. Every glitch becomes a fingerprint of that star's unique internal structure. Some of the best-studied glitches come from the Vela pulsar, a young and energetic neutron star about 1,000 light-years away. Vela glitches roughly every 3 years, with sudden jumps in rotation so large that astronomers first thought their instruments had malfunctioned. But the pattern was unmistakable. The star's superfluid interior was periodically shedding its stored angular momentum, jolting the crust forward in rotation again and again. Vela became the archetype of glitching pulsars, showing scientists that superfluid-driven glitches were not rare, but a natural part of neutron star evolution. Older pulsars glitch differently. Their crusts are cooler and more brittle, and their superfluid interiors behave differently. They glitch less often and by smaller amounts. Some slow their rotation so gradually that no glitch is observed for decades. Others, surprisingly, experience anti-glitches, sudden drops in rotation rate. These rare events may reflect magnetic field rearrangements or deeper changes in the star's moment of inertia. Millisecond pulsars, with their extraordinary rotational stability, glitch only rarely. When they do, the events are exceptionally small, revealing that their crusts and interiors are tightly coupled. Their superfluid layers have far fewer opportunities to drift ahead of the crust. Their evolution is slower, smoother, more uniform. Magnetars, the most magnetic neutron stars, glitch often and violently. Their extreme magnetic fields twist the crust continuously, driving fractures and internal reconfigurations. These emergent stresses can trigger glitches of unusual size and, in some cases, dramatic outbursts of X-rays or gamma rays. A magnetar glitch is not just a rotational event, it is a magnetic storm shaking a star to its core. Across all of these cases, glitches tell a story of tension, tiny differences in rotation accumulating over years, then releasing in a heartbeat. They tell us that beneath a neutron star's smooth exterior lies a dynamic, layered interior, alive with quantum motion and structural strain. They tell us that even the strongest materials in the universe cannot remain static forever. They must bend, shift, and occasionally yield. And quietly, glitches remind us that neutron stars, for all their stability, are not eternal machines. They evolve, they cool, their superfluid layers change, their crusts fracture, their magnetic fields decay, their spin slows. Glitches are signposts on this long journey, moments when the internal tension becomes impossible to hide. Each glitch, small though it is, sends a whisper through the cosmos. It tells us that the neutron star is still alive in its own quiet way, still adjusting to the tension between gravity, quantum mechanics, and magnetic force, still balancing itself on the edge of collapse and stability. And as we follow those whispers, one question naturally rises. If glitches expose the tension and energy stored inside a neutron star, what happens when that energy is released on a scale far greater than a mere rotational jump? When two neutron stars collide and unleash the birth of heavy elements? That is where our journey drifts next. Part 12. When neutron stars merge, the quiet birth of heavy elements. Every atom of gold, platinum, and uranium on Earth was forged in the collision of two neutron stars. When they spiral inward and merge, the resulting explosion, called a kilonova, creates the heavy elements that fill planets, oceans, and living cells. These stars that shouldn't exist become the factories of the universe's rarest matter. To understand how such extraordinary events unfold, imagine two neutron stars locked in a slow, spiraling dance. They may have orbited each other for billions of years, born together in the wake of a massive supernova, bound by gravity, circling silently in darkness. With each orbit, they emit gravitational waves, tiny ripples in space-time that carry energy away. As energy drains, the stars drift closer, their dance tightening, the orbit shrinking in a long, slow embrace. What begins as centuries of quiet motion eventually becomes an inward spiral measured in years, then months, then moments. As the neutron stars approach one another, their gravitational fields begin to distort each other's shapes. Tidal forces stretch their crusts. The superfluid interiors respond with shifting vortices, currents, and stresses that ripple outward. At this stage, the stars are so close that their magnetic fields interact, intertwining in a storm of invisible structure. Charged particles are accelerated along these fields, generating bursts of radiation. But the most important changes remain hidden, deep inside, where matter is compressed to densities that blur the line between particles and fluid. Just before merging, the neutron stars are orbiting each other dozens or hundreds of times per second. Their gravitational waves intensify. If you could listen to them, if your ears could hear the trembling of space-time itself, the sound would rise in pitch, from a faint thrum to a sharp chirping crescendo. This chirp is what detectors like LIGO and Virgo capture, the final heartbeat before the stars collide. The moment of impact is both catastrophic and extraordinarily creative. When the crusts finally meet, they shatter instantly. Nuclear matter from each star is flung outward, escaping the dense gravitational grip. This matter decompresses as it travels, and in that decompression, alchemy begins. The material ejected from the merger is made of neutrons, vast streams of them, far more than any normal environment allows. And where neutrons are abundant, a special process unfolds, rapid neutron capture, known as the R process. In the R process, nuclei absorb neutrons faster than they can decay. This rapid accumulation produces unstable isotopes that quickly transform into heavier elements. Gold forms this way. So do platinum, uranium, thorium, and dozens of other rare elements. These elements are not formed in ordinary stars, nor in supernovae alone. They require the extreme neutron-rich environment of merging neutron stars, a brief, violent chemistry lab where the universe forges its heaviest building blocks. The explosion that follows this creation is called a kilonova, an eruption roughly 1,000 times brighter than a classical nova, though dimmer than a supernova. Its glow is powered not just by heat, but by the radioactive decay of the newly formed elements. As these heavy nuclei decay, they release energy that shines outward across the galaxy. For days or weeks, the kilonova glows in hues of blue, violet, and red, its color changing as the radioactive isotopes fade. And then the light dims, leaving behind a remnant, either a heavier neutron star or a newborn black hole. The debris thrown into space, dust enriched with precious metals, spreads slowly through the cosmos. Over millions of years, it drifts, cools, collapses, and eventually integrates into new clouds of gas. These clouds give birth to stars, planets, and, in rare cases, worlds like ours. The gold in every ring and necklace on Earth, the uranium deep in the planet's crust, the platinum used in our electronics, all of it began as neutron star debris flung into space in a single ancient collision. Sometimes, astronomers can trace this ancestry. Chemical signatures in old stars show the telltale fingerprints of our process elements. Certain regions of the Milky Way contain stars enriched with heavy metals, indicating that a neutron star merger occurred nearby long ago. In this way, neutron stars leave a legacy far beyond their own existence. They seed the galaxy with the raw materials that allow planets to form with diverse compositions, including the elements necessary for life. The discovery of a kilonova in 2017 offered humanity its first direct glimpse into this cosmic alchemy. Two neutron stars merged in a galaxy 130 million light-years away, producing gravitational waves detected by LIGO and Virgo. Seconds later, telescopes across the world spotted a faint flash of light, then a rapidly evolving glow. Over the next days, the spectrum changed in ways that matched predictions for freshly synthesized heavy elements. For the first time, we saw the birth of gold and platinum as it happened, an observation that confirmed decades of theoretical predictions. But the violence of these mergers does more than create elements. It also reshapes space-time itself. The gravitational waves produced during the final moments of the merger carry information about the star's interiors, their stiffness, their composition, the behavior of matter at nuclear densities. Subtle differences in the waveform reveal whether the neutron stars resisted tidal forces or deformed easily. These clues help scientists refine their understanding of the neutron star equation of state, the mathematical description of how matter behaves under extreme pressure. In the aftermath of a merger, the remnant object may exist briefly as a hypermassive neutron star, a rapidly rotating, incredibly hot object barely stable under its own mass. This transitional stage lasts milliseconds to seconds. In this brief window, the remnant emits winds of neutrinos, magnetic fields twist into new configurations, and the superfluid interior undergoes rapid changes. Eventually, if the remnant exceeds the maximum mass a neutron star can support, it collapses into a black hole. If not, it settles into a stable neutron star, spinning fast and radiating away the heat of its formation. The physics governing these post-merger remnants remains one of the most active areas of astrophysical research. Simulations show that the interior motions, superfluid vortices, magnetic instabilities, shock waves, may influence the distribution of heavy elements and the structure of the kilonova's ejecta. Even the geometry of the explosion depends on the star's internal physics. Some mergers produce polar jets that race outward at nearly the speed of light, creating brief gamma-ray bursts. Others produce more spherical ejecta, glowing quietly in infrared light. But perhaps the most profound aspect of neutron star mergers is their role in cosmic evolution. Without them, the universe would contain almost no heavy elements. Planets would be barren worlds without the metals necessary for chemistry, geology, or complex biology. The Earth itself would lack the elements that make its core magnetic, its crust fertile, and its oceans rich in trace minerals. Even the DNA inside every living cell relies on elements forged in these ancient collisions. In this sense, the quiet birth of heavy elements is not just a cosmic event, it is part of our own origin story. Every human being carries atoms that were once trapped inside neutron stars, compressed into unimaginable densities, then flung across the galaxy by forces powerful enough to reshape spacetime. And so, when neutron stars merge, the universe becomes a little richer. Matter that was locked away for billions of years is released. Elements that enable life, technology, and planetary diversity scatter into the interstellar medium. The galaxy grows more complex, more diverse, more capable of supporting worlds like ours. As we reflect on these quiet factories of the cosmos, a gentle question moves to the forefront of our journey. If neutron stars can forge the universe's heaviest elements through collision, what becomes of the remnants left behind? Those quiet objects balancing on the threshold between stability and collapse? This question carries us naturally into the next chapter. Part 13. The sound of a neutron star. If we could hear gravity. When neutron stars collide, they send ripples through space-time itself. These gravitational waves, first detected in 2017, vibrate the universe with a pitch and rhythm far below anything we can hear. But if translated into sound, their waves would resemble a soft chirp rising in frequency, a quiet signature of cosmic destruction and creation. To imagine this sound, begin with the understanding that space is not silent in the way we usually think. There is no air, no medium for sound waves to travel through. But the fabric of space-time can ripple, and those ripples carry information with them. They stretch and compress the distance between objects, altering the rhythm of clocks and the length of rulers in ways nearly impossible to detect. Only instruments of extraordinary sensitivity, like LIGO and Virgo, can feel these waves, measuring distortions smaller than the width of a proton. Yet, in these subtle tremors lies the echo of cosmic events far more powerful than any other known phenomenon. When two neutron stars orbit one another, they emit gravitational waves continuously. Each orbit sends out a tiny pulse of space-time distortion. At first, these pulses are faint, slow, and nearly steady, like the quiet ticking of a clock in another room. Over millions of years, the stars spiral closer, tightening their orbit. As they do, the frequency of the waves increases, the rhythm accelerates. What was once a slow pulse becomes a rising beat, like the faint sound of a distant engine drawing nearer. If our ears could convert gravitational wave frequencies into audible sound, we would hear a continuous rising tone, a soft ascending whistle. This chirp is not poetic shorthand. It is literally the term scientists use to describe the signature of enspiraling neutron stars. The pitches increase rapidly in the final seconds before collision, climbing higher and faster as the stars whirl around one another dozens or hundreds of times each second. Then, suddenly, the sound stops. The waveform cuts off sharply. In that instant of silence, the stars merge and vanish into a new form, a hypermassive neutron star or a black hole, and the gravitational waves change character, becoming a fading hum too low to detect. This chirp is more than a sound. It is a record of the physics inside the neutron stars. Every twist, every deformation, every response of matter to tidal forces shapes the waveform. The star's internal structure, whether they contain hyperons, quark matter, or exotic states we have not yet imagined, determines how they behave in the final moments. By studying the waveform, scientists can probe the inner workings of neutron stars in ways no telescope or particle accelerator can match. Long before these collisions reach their final crescendo, the stars experience tidal stretching. Just as the moon pulls on Earth's oceans, each neutron star pulls on its partner. But here, the tidal forces are unimaginably strong, capable of deforming even nuclear matter. These deformations leave subtle imprints on the gravitational wave signal, altering its shape. Observing these distortions helps physicists refine their models of the neutron star equation of state, how matter behaves at extreme densities. The gravitational waves we detect are not merely signals, they are stories. They tell us the masses of the stars, their orbits, their spins. They tell us how stiff their matter is, how easily they deform, how much energy they radiate. They allow us to hear the universe in a way that was impossible before 2015, when the first gravitational wave was detected. But neutron star collisions are not the only events that create these waves. Even isolated neutron stars, spinning alone in the dark, may produce faint gravitational murmurs. If a neutron star has a small deformation, perhaps a tiny mountain only centimeters tall, its rotation will generate continuous waves. These waves would be far quieter than the explosive signals of mergers, but still present, humming softly through the cosmos. Detecting them would reveal imperfections in the star's crust and offer clues about its internal structure. Some neutron stars, especially magnetars, may produce gravitational waves during starquakes. When magnetic fields twist and snap the crust, the sudden shift in mass distribution can send waves outward. These events would produce short bursts rather than long chirps, and though none have been detected yet, they remain promising targets. But the most dramatic gravitational waves remain those generated by mergers. These events not only produce the chirp, but also a brief ringdown, the fading vibrations of the remnant object. If the remnant is a black hole, the ringdown reflects the final settling of the event horizon into a stable shape. If it is a hypermassive neutron star, the ringdown encodes information about extreme densities, rapid rotation, and intense magnetic fields. Listening to gravitational waves is unlike listening to any ordinary sound. There is no medium vibrating, no pressure wave moving through air. Instead, the listener is the universe itself. Distances stretch and contract in rhythm with the waves. A detector does not hear in the conventional sense. It feels the changes in length between its arms, interpreting those changes as sound. Scientists can then convert this signal into audio, scaling the frequencies into the human hearing range. What emerges is haunting. A soft, rising chirp, followed by abrupt silence, a cosmic breath drawn in and then released. The quiet aftermath of stars that have given everything they contain, matter, energy, heavy elements, back to the universe. The 2017 detection of a neutron star merger produced one such chirp, a brief but profound signature. For the first time, scientists heard a gravitational wave event and then saw its electromagnetic counterpart, a kilonova flash, moments later. This multi-messenger observation revealed the full story of the merger, the inspiral, the collision, the creation of heavy elements, and the aftermath. It marked the beginning of a new era, where the cosmos can be observed through multiple senses. Light shows us the surfaces of stars, the glow of galaxies, the remnants of explosions, but gravitational waves show us motion, pure motion, revealing the invisible dance of the universe's most massive objects. If we could listen without instruments, if our ears could feel the trembling of space-time, the universe would be filled with faint echoes. Black hole mergers would sound like deep thumps. Neutron stars would create soft, rising whispers. The cosmos would become a symphony of gravity, each note shaped by mass, spin, distance, and density. And yet, even with all we have learned, many mysteries remain. Gravitational waves carry hints of exotic matter, of phase transitions deep within neutron star cores, of hypermassive remnants held together by rotation. They suggest that even more extreme events lie waiting in the darkness, collisions involving black holes and neutron stars together, or perhaps signals from the very early universe. Every chirp adds a new voice. Every detection expands the universe we can perceive. And as we listen to these gravitational murmurs, one question follows softly. If neutron stars can sing through space-time, what else can their behavior teach us about the boundary between matter and collapse? About the point where a neutron star becomes too massive to endure? That quiet threshold leads us into the next chapter. Part 14. The strange question at the heart of neutron star. Physics scientists still don't know what lies at the very center of a neutron star. It might be quark matter, loose quarks roaming freely. It might be hyperons, strange particles formed under extreme pressure. It might even be something we have no name for yet. The deeper we go, the more neutron stars challenge our understanding of matter. To explore this mystery, imagine peeling away the layers of a neutron star as if descending through a geological core sample, except each layer becomes stranger than the last. At first, we pass through the crust, rigid and crystalline, stronger than any material known. Then, we move into the superfluid ocean of neutrons, a domain where quantum mechanics shapes motion, where friction ceases to exist, and where rotation organizes itself into perfect vortex arrays. But if we descend further, miles into the interior, we confront something far more uncertain. The pressures rise to levels beyond human comprehension. Density climbs to 10 times that of ordinary atomic nuclei, perhaps more. At such extremes, the familiar boundaries between particles begin to blur. It is here, in this deepest region, that the known laws of physics lose their clarity. Neutrons, normally stable only when bound inside a nucleus, may be crushed so tightly that they begin to dissolve. In their place, new forms of matter may appear, forms that exist nowhere else in the universe. This possibility is the strange question at the heart of neutron star physics. What is matter when it is compressed beyond the limits of its identity? One answer proposes quark matter. Neutrons and protons are made of quarks, tiny, point-like particles bound together by the strong nuclear force. Under normal conditions, quarks are confined, held tightly within neutrons and protons by a force so strong it prevents them from escaping. But at densities and pressures found at the center of a neutron star, this confinement might break. Quarks could spill into a shared ocean, moving freely in a kind of exotic soup. This deconfined quark matter would be utterly unlike anything on Earth. It would be a fluid made not of atoms or even particles we can isolate, but of quarks themselves, a state of matter that likely existed only in the first microseconds after the Big Bang. If quark matter exists in neutron star cores, it could take several forms. It might be a simple quark-gluon plasma, similar to what particle accelerators create for fleeting moments. But the core of a neutron star is cold compared to the early universe, and cold quark matter may behave differently. Some theories predict that quarks could pair up in unusual ways, forming color superconductors, states where quarks align in coordinated frictionless currents, similar in spirit to how electrons pair in superconducting materials on Earth. Others suggest even more exotic arrangements, such as strange quark matter, where up-down and strange quarks exist in equal measure, forming a stable form of dense matter that might be more stable than nuclear matter itself. Another answer suggests hyperons, particles that contain strange quarks, cousins to neutrons and protons that normally decay quickly on Earth. Under extreme pressure, however, decay becomes impossible, and hyperons may fill the core. These particles would allow matter to pack more tightly, softening the equation of state. But there is a problem. If hyperons appear, their formation tends to reduce the pressure that resists gravity. The star could collapse more easily into a black hole. And yet we observe neutron stars with masses around 2 suns, far heavier than early hyperon models predicted. This discrepancy between hyperon-rich models and observed neutron star masses is known as the hyperon puzzle. Solving it may require new physics, new forces, or new interactions that we do not yet understand. A third answer, more elusive, proposes that the core may harbor matter so exotic that we lack even the vocabulary to describe it. New particles, new interactions, or unknown quantum phases may arise, phases that only reveal themselves under the most extreme circumstances the universe can provide. Some theorists speculate about pasta phases, where nuclear matter arranges itself into sheets, rods, or even labyrinths of neutrons and protons. Others imagine crystalline quark phases, solid quark matter lattices that behave like minerals at the heart of a star. Still others believe the answer lies not in exotic matter, but in a deeper understanding of how ordinary nuclear forces behave when pushed to their absolute limits. The strong nuclear force is well understood at ordinary densities, but compress it tenfold, 100-fold, and its properties may shift in unexpected ways. Forces that are negligible in atomic nuclei may dominate in neutron star cores. Three-body interactions, where the presence of a third particle alters the forces between two others, may become critical. New symmetries may emerge, and the interactions may not resemble anything we can model on Earth. What makes all of this so challenging is that we cannot probe neutron star cores directly. We cannot sample them. We cannot recreate their conditions in any laboratory. Instead, we rely on indirect evidence, clues carved into the star's mass, radius, rotation, cooling, and gravitational wave signatures. Each observation narrows the possibilities, peeling away layers of uncertainty. Gravitational waves, in particular, offer new insight. When two neutron stars merge, their tidal deformation affects the waveform. A stiff equation of state, a core that resists compression, produces a different tidal signature than a soft one. The wave's shape tells us whether the stars deform easily or stubbornly hold their form. These details hint at what lies within. Already, gravitational wave observations have ruled out some models of hyperon matter and some versions of quark cores. But they have not delivered a decisive answer. They whisper, but do not reveal. X-ray observations help as well. By measuring how hotspots move across a neutron star's surface, distorted by the star's intense gravity, scientists can infer its radius. A larger radius suggests a stiffer core. A smaller radius suggests a softer core. Observations so far have revealed neutron stars in a narrow range of radii, around 11 to 13 kilometers. This range supports some theories and excludes others, but it does not single out one definitive model. Even the star's cooling rate carries clues. Neutron stars lose heat through neutrinos streaming from their interiors. The type of matter in the core determines how quickly this cooling occurs. Superfluid neutrons cool differently from quark matter, which cools differently from hyperons. Some young neutron stars cool faster than expected, hinting that exotic processes, possibly involving quarks, may be at work. But uncertainties remain, and nature rarely reveals its secrets all at once. The heart of a neutron star is inaccessible not just physically, but conceptually. It operates at the intersection of quantum mechanics, general relativity, and nuclear physics, an intersection where our models strain. Matter behaves as both fluid and particle. Gravity curves space enough to alter pressure. Quantum effects stretch to macroscopic scales. The smallest components of matter battle the largest force in the universe. It is a collision of extremes, and in that collision lies the central mystery. What is matter when gravity compresses it beyond the limits of our knowledge? Is it quarks, hyperons, something stranger? Or is it a new state of matter waiting to be discovered, a state that only neutron stars and nothing else in the cosmos can create? This question remains open, quiet, and profound. It sits at the boundary of what we know, inviting us forward. And as we approach that boundary, one more question follows gently. If the center of a neutron star holds the unknown, what happens to that secret when a neutron star grows too massive to sustain itself? When it crosses the final threshold and becomes a black hole? That is where our journey leads next. Part 15. Why neutron stars shouldn't exist, and what their existence tells us. According to our earliest theories of gravity, matter, and collapse, a star dense enough to crush atoms should continue collapsing forever. And yet, neutron stars stop at the brink, balanced by forces that emerge only at nuclear scales. Their existence is a quiet reminder that nature still hides laws we don't fully understand. Laws written in pressure, in density, and in the limits of what matter can endure. To understand why neutron stars remain one of the universe's most improbable successes, imagine following the logic of classical physics alone. For centuries, gravity was seen as a force with a single, uncompromising tendency: to pull. According to Newton, if enough mass accumulates in one place, no amount of ordinary pressure can support it. The material would collapse inward, each layer pressing down on the one beneath it in a tightening spiral of compression. In this view, once a star's fuel was exhausted and its internal heat faded, gravity would have the final word. It would draw the star inward without limit, compressing matter until no known structure could hold. In this framework, neutron stars should simply not exist. They are too dense, too compressed, too extreme. The pressure inside them should not be able to halt collapse, but the universe cared little for our expectations. Neutron stars not only form, they persist, sometimes for billions of years. Their existence marks the moment when the classical picture breaks and quantum physics takes over, revealing forms of pressure and structure that emerge only when matter is pushed to extremes. The first of these forces is neutron degeneracy pressure. It arises from the Pauli exclusion principle. which states that identical fermions, particles like electrons and neutrons, cannot occupy the same quantum state. As matter is crushed, neutrons are squeezed closer and closer together, but they resist overlapping entirely. This resistance manifests as pressure, an invisible stiffness that emerges not from temperature nor from motion, but from the rules of quantum identity. It is a form of structural integrity foreign to our everyday experience, present only in dense objects like white dwarfs and neutron stars. But degeneracy pressure alone is not enough. At neutron star densities, the strong nuclear force comes into play as well. Under ordinary conditions, this force binds nuclei together, operating over distances smaller than atomic cores. Under neutron star conditions, it shifts roles. When neutrons are forced unnaturally close, the strong force becomes repulsive. It pushes back against compression, acting like a hidden barrier that prevents neutrons from collapsing into a single point. This repulsion, short-range, intense, and quantum mechanical, supports the star alongside degeneracy pressure, forming a hybrid equilibrium that no earlier theory predicted. These forces, combined, create a razor-thin threshold. If the star's mass is below a certain limit, neutron pressure and nuclear repulsion hold. If it is above, collapse resumes and nothing can stop it from becoming a black hole. Neutron stars exist in the narrow space between these outcomes, not massive enough to collapse outright, not light enough to remain as white dwarfs. They are cosmic tightrope walkers, balanced at the edge of physical possibility. Their existence challenges our models in other ways too. For example, neutron stars should cool far faster or far slower depending on their internal composition, and yet observations show a cooling pattern that doesn't neatly match any single prediction. Some stars cool rapidly, suggesting exotic particles or direct neutrino emission processes. Others cool more slowly, hinting at superfluidity or superconductivity deep within. The variety is unexpected. It suggests that neutron stars may host multiple interior phases, with different stars revealing different possibilities. Their magnetic fields also defy simple explanation. Magnetic flux conservation explains why the field strengthens during collapse, but it does not explain why some stars are born with fields trillions of times stronger than others. The existence of magnetars, neutron stars whose magnetic fields can twist their crusts and trigger violent outbursts, indicates that something in their birth conditions, rotation rates, or internal convection processes creates engines vastly more efficient than any model anticipated. Then there is their rotation. Newly formed neutron stars can spin a few dozen times per second, but some millisecond pulsars spin hundreds or even 1,000 times per second. These rotational speeds require extraordinary stability and reveal the intricate transfer of angular momentum between the crust and the superfluid interior. The existence of such rapid rotators shows that neutron star matter behaves not like a rigid solid or a normal fluid, but like a quantum system on astronomical scales, frictionless, ordered, and governed by principles normally confined to laboratories. Even their mass distribution presents a puzzle. The heaviest neutron stars observed, approaching or exceeding 2 solar masses, press against the theoretical limits of stability. Yet, they do not collapse. Their survival suggests that the equation of state, the mathematical relationship between pressure and density, is stiffer than some models predict. But if it is too stiff, it contradicts observations of smaller neutron stars and gravitational wave signatures from mergers. The result is a tension in our theories. The very existence of both light and heavy neutron stars implies a complexity in nuclear matter that we have not yet pinned down. Their radii, too, rest in a narrow range. Observations indicate neutron stars are typically 11 to 13 kilometers in radius. But variations in temperature, age, magnetic field, and internal composition can modify these measurements. The fact that so many neutron stars fall into such a consistent band suggests a universal behavior of nuclear matter, one that emerges naturally under extreme compression. Yet we do not fully understand why. What is special about this density? What quantum arrangements occur there that dictate a radius so precise? The more deeply astronomers examine neutron stars through X-ray timing, gravitational waves, thermal emission, pulsar glitches, and rotational evolution, the more contradictions arise between theory and observation. Each new detection opens another door into fundamental physics, revealing subtleties that our current models cannot predict. Neutron stars should not exist according to classical gravity alone. They should not hold their shape. They should not resist collapse. They should not host superfluid layers or superconducting cores. They should not remain stable while spinning hundreds of times per second. They should not create magnetic fields strong enough to warp the vacuum or produce starquakes that shake the crust. And yet they do. Their persistence forces us to accept that our current picture of matter is incomplete. It pushes scientists to refine nuclear physics, quantum chromodynamics, and the theory of gravity. Neutron stars stand at the intersection of these fields, where each theory must confront its limits and merge with the others. In this way, they act as laboratories, natural experiments running continuously across the galaxy. They remind us that the laws of physics are not merely equations written in books, but living descriptions of how matter behaves under every possible condition. Neutron stars explore conditions humans cannot replicate, pressures greater than atomic nuclei, densities that blur the distinction between particles, magnetic fields capable of distorting quantum vacuum. They give us glimpses into what matter becomes when pushed beyond imagination. And they hint that somewhere between neutron degeneracy and black hole collapse lies a frontier of unknown physics, a frontier where quarks may roam, where new particles may form, where new symmetries may emerge, and where gravity and quantum mechanics may intertwine in ways we have not yet conceived. Neutron stars exist at this frontier. They survive where collapse should reign. They stand where theory falters. They reveal that even in a universe ruled by gravity, there are counterforces, silent, quantum, and deeply mysterious, holding their own against the darkness. And as we reflect on these stars that shouldn't exist, yet do, one final question drifts into view. What does their improbable survival tell us about the universe itself, about the balance it maintains, the mysteries it preserves, and the quiet forces it hides in the heart of matter? That gentle question guides us into the outro, where we reflect on the journey we have taken.